Okay, so now that we sort of understand how to set up a DMA transfer in the context of the Linux kernel, I am going to look at a couple of examples of how do we do comparisons of the performance of DMA versus other kinds of ways of transferring data. And so initially start off with a couple of qualitative considerations and then look at some numerical examples, right. So there are, broadly speaking, some related concepts over here, right, polling, interrupts and DMAs. Now what I mean by polling is when I am actually trying to, let's say, transfer data into or from one chunk of memory locations to another. Here the CPU basically is going to read data, a load operation, increment the address, then perform a store operation, increment the address, then increment a counter, then go back, perform the branch and so on. Every sample is being loaded, stored one by one through MMIO, right. The interesting thing is, even though it sounds like the CPU is busy and so on, this will actually have the lowest control latency, because even though I say load, increment address, store, increment address, from the point of view of any other code that is required, there is almost nothing. I am exactly doing what I need. I just load the data, store it into the appropriate location, right. I am not sort of setting up a bunch of DMA registers, then waiting for an IRQ, running an IRQ handler and so on. So this potentially has the lowest control latency, but the CPU is clearly going to be busy. Okay. Now if I only wanted to transfer, let's say, one word of data, it's a no-brainer, this is what you use, right. But let's say I wanted to transfer 10 words of data, it's not so obvious, right, because maybe constantly keeping the CPU loaded for that makes no sense. What about 1000 words of data? Almost certainly this starts to sound like a bad idea. At that point, interrupts and DMA sort of work together to sort of see if we can do something better, right. Now I could potentially do something else, which is that I have something where the CPU is sort of doing some data transfer, let's say into the FIR filter, right. I transfer the data, but then after that, while the FIR filter itself is working, I go into sleep mode, right. Over here, not only do I sort of transfer all the data, I then need to sit and poll and wait for the FIR filter to complete. Whereas over here I could potentially say, okay, copy the data, send a chunk of data and then go to sleep. The IRQ will wake you up once the FIR filter is done, right. So the data move cost itself is the same over here, I haven't really solved that problem, but potentially the CPU load is less because I don't need to sit there waiting for the filter to complete, okay. Or if it's something more complex like an FFT or something, the FFT might actually take hundreds of cycles. During that time the CPU could either sleep or do something else. DMA at this level at least potentially has the best solution, right. It configures the descriptors, addresses, and then the CPU goes to sleep or does something else, right. It context switches and starts working on something else. The hardware performs bulk transfer, and it after the FIR filter has completed and the data has got transferred back into the memory, only then will the CPU get woken up, right. Or at least I can set it up that way. I can set the CPU up to completely ignore interrupts from the FIR filter. In fact, there won't be interrupts from the FIR filter because it's now in streaming mode, right. The interrupt will come only from the DMA engine. Typically you will get a higher throughput and the overhead on the CPU is minimal, right. The issue is this part. I need to configure a bunch of descriptors, right, which are basically all the addresses and the DMA alloc coherent and setting up the buffers and all of those things, right, which is potentially overhead, which means that if I need to transfer only a few words, then it probably doesn't make sense. So MMIO, in other words, is throughput limited by transactions at an individual register level. It scales poorly. As the number of transfers that you are doing increases, it starts running into problems. Now the DMA can actually get to a point where the throughput is dominated by the bandwidth of the bus itself, right. That's usually the best case scenario, right. If you are able to, as they say, saturate the bus by making sure that there is a data transfer on every clock cycle, that's the best that you can do, right. So therefore, we can sort of usually imagine that in most cases, especially for large buffers, DMA is going to be much faster than MMIO. So let's sort of see if we can put some numbers on it, right. So just a word of warning, these numbers, every number that I have over here is more or less a made up number, right. It is not an actual practical value that has been measured in any scenario. I have chosen these numbers in such a way that it allows me to illustrate, okay, at what point does it make more sense to use MMIO versus DMA and so on, right, and to also show you what are the potential scenarios in which you might prefer one over the other. In reality, every microcontroller, every bus, every SoC will have a different set of trade-offs that you have over here. The numbers will change and you will actually need to know what are the numbers for the scenario that you are dealing with in order to make appropriate decisions. So with that in mind, let's sort of work through this. Let's first start off with the assumptions on our system, right. I will assume that I basically have one MMIO per 32-bit operation and that the time for this is 250 nanoseconds, right. Sounds like a lot. It is if you are working with, let's say, a 1 GHz processor. Not so much if you are working with, let's say, a 100 MHz processor where this is around 25 cycles. This is still not trivial, but on the other hand, it's more reasonable because I need to read, increment, write a bunch of things over there. 25 cycles is potentially possible, right. We already saw that the axis write could potentially take like 5 or 6 clock cycles and so on, right. So MMIO, I'm going to assume that it takes 0.25 microseconds per sample, which means that if I want to do a write and a read, I'm going to require 0.5 microseconds. Okay. Now the DMA, the first thing is I have something called setup. What is the setup? It basically means making sure that the buffers have been allocated properly. They are pointing, because if I am normally, what I would do is every time I want to do a DMA, I need to allocate the buffers with the correct pointers and the physical addresses and so on. So it takes time to do that. I then need to go and write appropriate values into all the registers so that they are set up properly. And then I'm going to assume that I have an effective bandwidth, capital B, of 50 megabytes per second. Now this capital B is probably a bit confusing because this B has nothing to do with the byte over here, so please keep that in mind. This is just a parameter B, the effective bandwidth of the bus. 50 megabytes per second, how did I come up with a number like that? I'm assuming that the DMA is capable of this, right. Maybe it is actually working with some kind of a bus which is working at 12.5 megahertz effective bandwidth and maybe a 32-bit transfer on every clock cycle, or it might be that it actually needs to do a read followed by a write and so on. But remember that it's definitely not going to be the same overhead as what is there in the case of the axis light, right. So if you look carefully at the numbers, you will realize that this effective bandwidth over here is much better than the effective bandwidth that you can get from this, right. Think about it. If I have like 0.5 microseconds for a read, write followed by read, that basically limits my effective bandwidth to 2 megabytes per second, right, or 2 into 4, so 8 megabytes per second, because I can transfer 4 bytes in one write plus read, so 8 megabytes per second, right, whereas the DMA I assume is capable of doing 50 megabytes per second. So what that means is, in the case of the DMA, right, if I have a in and out the round trip of data, I'm going to assume that just like this, a 32-bit data, I basically have like 4 divided by B, or 0.08 microseconds to actually transfer the data, right. So in other words, when I say effective bandwidth, I'm assuming that it is actual copy bandwidth. I have managed to take the data and transfer it. Okay. What that means is I can now put together a sort of model of computation which says that the time taken for MMIO of n words in this case, right, is going to be n into 0.5 microseconds. In the case of DMA, it's going to be the setup time 5 microseconds plus n into 0.08, because 0.08 was the time for one word to be transferred. Okay. And finally, let's leave aside this and we'll come back to this. Let's take these examples. right? If I do the computation, what it means is that with n equal to 8, the T MMIO is going to be 4 microseconds, n into 0.5, right? With DMA, it is going to be 5.64 microseconds because 5 microseconds just for setup and 0.64 microseconds for the actual transfer, right? Now in reality the DMA would also have the IRQ and the response and so on, but I am sort of clubbing everything together in this 5 microseconds and saying that is part of the setup associated with DMA. What about n equal to 16? At this point you can already see that the time for MMIO is 8, the time for DMA is 6.2 or 6.3, DMA has already become a little faster. But this is one of those unknowns where we could argue that if the extra overhead associated with actually setting up DMA, programming the DMA and so on is not worth it, right? Don't bother, just basically get it figure it out with MMIO simply because the code is easier to write. But when you get to n equal to 64, the story is completely different. MMIO takes 32 microseconds, DMA takes 10. At this point DMA is clearly faster and you really have to justify why you would still want to use MMIO instead of DMA. If you sort of just link both of these equations together, you can sort of work out an n star, which is the break even point, right, where we can say that at what value of n do we get that these two numbers are almost equal, and by working it out you will see that that's basically at 5 divided by 0.5 minus 0.08, which is about 12, okay. So in other words, for, as you can see over here, when it went from 8 to 16, we found that DMA seemed to have got better. Actually at 12 is when you are going to find that the numbers are almost equal, right, and that essentially that's the sort of tipping point when we switch from one to the other, right. So in other words, what we have over here is a scenario with fairly modest setup costs. This 5 microseconds, if I compare it to the time for an MMIO, right, 5 is not very large, it's just sort of 10 times the the equivalent of writing 10 values in MMIO, and that is more or less what we saw for the break even point over here, right. So it ultimately comes down to that if my MMIO is somewhat slow because of my axi light overheads and so on, and at the same time my DMA setup is not very complicated, then even for n equal to 16 it makes sense to use DMA. That's not always the case. Very often we find that the scenario is actually slightly different. The time for MMIO is probably even less, let's say 0.3, I have not reduced it a whole lot, just a little bit. But now the DMA setup takes 30 microseconds. Now look at the difference, instead of 10 times this is 100 times, right. So the DMA setup takes effectively the time for 100 data transfers out here, right. The effective bandwidth of DMA is actually higher, right. I am going to assume that it's 100 megabytes per second. So the DMA, and after all the MMI also became faster, but the DMA is even faster, right. But when we finally work through this n into 0.3, 30 plus n into 0.04, we find that the break even is still at somewhere around 116, right, and you can actually check that out. For n equal to 64, MMIO is faster, 128, DMA is slightly faster. By the time you hit 512, the DMA is like 3 times as fast, right, and it's only going to get better from there. So if I want to transfer like a few kilowords, then no question about it, the DMA is obviously going to be much better, right. This is a scenario where the setup time is higher, it has a higher setup latency. And keep in mind, I don't care about this raw number, I don't care that this was 30 microseconds versus 5 microseconds. What matters is this is 30 microseconds when compared to the time for an MMIO op. This is nearly 100 times of this, right. That is what I mean by higher setup latency, right. So if instead what we were talking about was that this was actually something like 20 nanoseconds for a transfer and this was also some few nanoseconds, yeah, all the calculations would change accordingly, right. These numbers are probably reasonable for not just a microcontroller, because after all mostly we are talking about a Linux kind of a system. There are overheads associated with interrupts, with just setting up the OS, with configuring things and so on, which would mean that these numbers are probably not too far from what you are likely to see in practice. So just to sort of put that together, the MMIO is n times just the time for one transfer. In DMA we have a big setup. Once again I want to repeat, this has nothing to do with setup and hold time in a digital system. This is the time for setting up the DMA, which means that the threshold essentially comes out to be this formula that we have over here. I would definitely not suggest sort of memorizing this formula. Please understand where you are working this out from, so that you should be able to see this even if it is a slightly more a slight variant of this, that is the actual way that DMA is configured. So the general rule of thumb, DMA should be used when n is much larger than n star, or if you must guarantee that the CPU must be free during transfers for whatever reason, right. MMIO on the other hand does make sense for very small n, or when you have rare and latency sensitive operations.